All right. Well, it's 8th week Wednesday. You guys take a collective deep breath or sigh after I said that. Okay. We will look at k-means clustering, or we looked at k-means clustering on Monday, and today we'll kind of expand it using kernel functions. And so if you remember, we had talked about kernel functions when we did SVM, and we said it projected our data into a higher dimensional space that allowed us to kind of create a linear separation. And here we're going to do something similar, except it's going to be used in the context of clustering. Okay, so first, just a quick review of the k-means clustering algorithm. And so remember, in clustering, there is no labels. The data comes in. It's unsupervised learning, right? So the data just comes in. There's no labels or anything. And you're asking the algorithm to find structure, to kind of group points that are similar to each other. And so that's what we do. And we're going to we start off the thing that you need to do is you need to specify how many clusters you're looking for. So we're going to say, let's look for 3 clusters or 2 clusters or 5 clusters, whatever. We randomly assign the points to each cluster just at random. So the initial assignments are totally random. And then once you've assigned the points randomly, you're going to calculate the centroids of, for each kind of group. And once you do that, you calculate your centroids, and then you reassign the points to the nearest centroid, and then you iterate back and forth between recalculating the centroids and reassigning points. So here is some data coming in. They come in, and we just start off with random assignments. Okay, so we just have the points randomly assigned to either black, red, or green. Black, red, or green, randomly assigned. And then we say, okay, tell me what is the centroid of all of the points assigned to black? What is the centroid of all the points assigned to green? What is the centroid of all the points assigned to red? And because of randomness, they are not exactly the same. They're kind of all near the middle, which is what we would expect. But again, because of randomness, some points, there's a difference between these things. Okay, and then we just say, all right, which points are closest to black, which points are closest to red, which points are closest to green. And so we reassign, and basically all of these points over here will be close to black. All of these points over here will be close to red, and then some points will be closest to green. Okay, so green only gets maybe like these 3 points. Okay, and that's just a coincidence of the data. And then so we say, okay, now that we've reassigned all the points to each of these clusters, let's calculate the new centroids. What is the center of all of the points assigned to black? What is the centroid of all the points assigned to green? What's the centroid of all the points assigned to red? And so when we do that, this is what we get. So the centroid, or the mean of all of the points assigned to black, is over here. The centroid of the 3 points assigned to green is down here, and the centroid of all the points assigned to red is up here. Okay, and now we go through and we reassign points. We say, okay, whichever centroid is the closest, that's where we will assign the points. So now a bunch of points down here will get assigned to green. Okay, and I'm not sure how many will change, but these points now get assigned to green. A few points over here got assigned to red, and these pretty much stayed over here. Now that we've done this, we recalculate what is the centroid of all of these points assigned to green, what's the centroid of all of the points assigned to red. And so the centroids will shift locations a little bit. Okay, and we just kind of iterate. We go back and forth. Once we've recalculated the centroids, we reassign the points. Okay, so we go from here to here. So we can see kind of our biggest change happens right here. And then once we do that, we recalculate the centroids. And so our centroids shift from there to there. And we go back and forth, and our centroids shift a little bit. And at this point, there's very little change from here to here. There's still a little bit, and so the centroids shift, but ever so slightly. And then at the next iteration, there's no change, and that indicates that we're done. Okay, so here's kind of the full process. Random points, calculating centroids, reassign, recalculate, reassign, recalculate, reassign, recalculate, reassign, recalculate, reassign, very little change, recalculate, and then there's no change from here to here, indicating that it has converged. And that's k-means clustering, okay? And that's that. And I hope that feels okay, okay? And again, the way we're deciding to assign points is we're just saying which point is the closest, and we say closest using Euclidean distance. Okay, today we're going to do the same thing, except now it is going to be kernelized, okay? And so the idea here, again with the kernel function, is there is some function that we can apply to 2 points, xa and xb, and the result of this kernel function is equivalent to applying some kind of transformation to the point xa and applying the transformation to xb, and then taking the inner product of those transformed points. And so we saw this when we did SVM. What we did was we took our point in 2 dimensions, and this transformation projected it into 3 dimensions, and then we took the inner product of those 3-dimensional coordinates. Right? If the transformation function is the identity function, then this just becomes the inner product of xa and xb, or the xa transpose xb. Okay. So if this function phi doesn't actually transform the coordinate, then we just have kind of the inner product of xa and xb. Okay, so here is one possible transformation and the equivalent kernel function. So here I'm going to say, let's have this function phi. It transforms from 2 dimensions into 3 dimensions. So x1, x2 goes and becomes x1, x2, and we add a third coordinate, x1 squared plus x2 squared. So this was the same transformation function we used in SVM, which took kind of the points, that video that you saw projected up into kind of the paraboloid and allowed us to draw a linear plane. We're doing the same kind of thing. If we transform xa and xb, okay, so xa consists of xa1 and xa2, and we transform it, then it will have the coordinate xa1, xa2, xa1 squared plus xa2 squared is its third coordinate. We do the same thing to the point xb, so we get xb1, xb2, and then the third coordinate is xb1 squared plus xb2 squared. When we take the kind of the dot product of this, we get xa1, xb1 plus xa2, xb2 plus xa1 squared plus xa2 squared times xb1 squared plus xb2 squared. And with a little bit of rearranging, we can see that this part, xa1, xb1 plus xa2, xb2, is the equivalent of kind of the dot product of xa and xb. And this part over here, which is the product of xa1 squared, xa2 squared times xb1 squared plus xb2 squared, is the product of basically the norm, xa norm squared and xb norm squared. Okay. So this kernel function is the equivalent of taking some coordinate in 2 dimensions, applying the transformation so it becomes a 3-dimensional point, and then taking the inner product of those 3-dimensional coordinates, or 3-dimensional vectors. Is that okay? Again, the review of the kernel function. Here's just another example of a different kernel function in a different transformation. So this one also goes from a point in two dimensions to 3 dimensions. So here we're going to take x, some coordinate, some point which exists in 2 dimensions, x1 and x2. And this transformation function could go to x1 squared, x2 squared, and root to x1, x2. And if you do this and apply it to the point xa and the point xb, and then you take the inner product of these two things, you'll get xa1 xb1 squared times plus xa2 xb2 squared plus 2 xa1 xa2 xb1 xb2. Okay, and this can be factored into xa1 xb1 plus xa2 xb2 quantity squared. Okay, this whole thing can be factored into that, and thus we can create a kernel function, or say this kernel function is the equivalent of doing kind of the inner product, or xa transpose xb quantity squared. Okay, so this is another example of a kernel function, and there's a lot more that here we've gone from 2 dimensions to 3 dimensions, but there's other kernel functions that would go from 2 dimensions to, say, 4 or 5 dimensional coordinates, and then you're taking the inner product of these 5-dimensional vectors. Okay, but again, whenever you take the inner product of 2 long vectors, you still just get a single scalar value at the end. Okay, which is neat. And so, technically the radial basis function, or the Gaussian kernel, technically it projects it into another vector that's of infinite length. Okay, an infinitely long vector, and that's very difficult to comprehend. Okay, and then kind of by magic, or not by magic, it's just when you take the inner product of 2 vectors that are infinitely long, you still get a single scalar value. Okay, and that's kind of the mystery and beauty of these kernel functions, is that we actually don't have to know what the transformation function is directly. Okay, we don't actually have to know this and project it into higher dimensions and then take the inner product. We can just go directly to the kernel function result and know that this is what we would get if we did go through the transformation. So it's like a shortcut that saves us a lot of kind of just mental energy, where we don't actually have to worry about what exactly is this phi function. That we just need to know it's happening kind of like behind the scenes, under the hood, or just mathematically it's the equivalent of doing this thing without actually having to do it, right? I think there is something kind of tangible about seeing it transformed into 3 dimensions or 4 dimensions or 5 dimensions, and then taking the inner product, and you know exactly where these numbers are coming from. But you can also just do this and you get the same results. Okay, and again, so here more kernel functions, so on and so forth. And what is the equivalent phi function? It's not actually necessary to figure out. All right, before I go on, let me give you your first view quiz answer for today, which is the letter A. A as in apple. A as in apple. Okay, so I think this is just saying what I said, which is we don't have to think of the transformation function itself. We just need to know that this is an inner product, and we can kind of take any kind of function that we have, and we can kernelize it by replacing some inner product in the original space with kind of this kernel function here. Okay, so this is what we are going to do. Okay, we're going to use kernel functions when we do k-means clustering. Okay, and so kind of the key idea is, in k-means clustering, the cluster assignments are entirely dependent on how far is each point to each centroid. Okay, so when we were the first example that we saw today, we said, okay, these points are randomly assigned to this centroid. We're going to calculate the location of the centroid. And now that we have that, we're going to reassign all of the points to the nearest centroid. Okay. If I just told you the location of the centroid, you can calculate the distance from point N to the centroid of cluster K, right? So if you have, if we're talking about, so D11 would be how far is the first point to the first centroid. D12 would be how far is the first point to the second centroid, so on and so forth. And basically that's just the distance, or xn minus mu sub k, so point n, point 1, minus the location of centroid k. We're going to just do x minus mu transpose x minus mu, right? And this is going to give us the squared distance to the centroid. And what is the location of mu k? Well, mu k is the mean of all of the points assigned to cluster k. So if a point x sub j is assigned to cluster k, z jk is 0, I mean is 1, and the z is 0 if it's not. Okay, so here we go through all of the points in our data set, and if it's assigned to the cluster, it's going to be a 1, and we're basically going to add these up and divide by how many points are assigned to cluster k, or and then if it's not assigned to the cluster, we zero it out. This the z is going to be a 0. So this is going to be the formula for what is the centroid of cluster K. All right. So using this, I'm going to substitute mu k with this thing. Okay, I'm going to replace the mu with this summation here, and that's what we're going to have on the next slide. So it's going to look crazy, okay, because I'm just replacing the mu's with this thing, okay? So I replace the mu's with this, I replace the mu's with this, okay? So I have xn minus, and then, the sum of all of the points assigned to cluster K divided by n sub k, and then transpose xn minus this. Here I have the summation with the subscript m, and over here I have the summation with the subscript r to indicate that these, because we're taking the product of these things, this summation has to be found independent of this summation. Okay, so that's why you're going to just see all of these different letters and subscripts. So we're going to say, all right, for all of the points from 1 to n, for m's, x sub m, we're going to find the centroid here. We're going to also do the same thing here. And then when you distribute, or when you multiply this out, you get xn transpose xn. And then you're going to get, what is this? Okay, so I'm going to take the inner, so I'm going to get this summation with xm times the xn, okay? And then you do the outer, so you're going to get this summation times xn, so xn times this summation. And then you get the product of the last two summations. So now you get this double summation with the subscripts m and r. I hope this feels okay, all right? And then these two things, as uncomfortable as it might feel, these are exactly identical, okay? These two things, we can combine them, because if you calculate this summation for all the values of m, it's going to be exactly equal to the summation if you calculate for all the values of r. So those two things can be combined into this, okay? So I'm just going to keep one of the letters, and it'll be the m. But it doesn't matter. I could have chosen the r as well. Okay, so we got xn transpose xn, the summation from each point xm to xn. So remember, this is the distance from point n. So when you're calculating this is, the n is one fixed value. We're finding what's the distance from the first point or the second point, whatever n is, to the centroid of cluster K. So n is a fixed value and n is kind of a fixed value when you're doing these summations. And then, yeah, we have this double sum, okay? And the product of all of these z's here. Okay, and basically this is the distance from point n to the centroid of cluster K expressed as kind of this weird combination of inner products and double sums and things like that. Okay, and the reason why we wanted to do this was so that we can apply our kernel functions. Okay, so we're going to just say, hey, we've got an inner product between xn and xn here. Let's just do the kernel function of xn and xn. Okay, we've got the inner product of xm and xn. Let's do the kernel function between these two things. We've got the inner product of these two things. Let's apply a kernel function there. Okay, and again, a kernel function is we're going to take our point, transform it into a higher dimension, and take the inner product. And this allows us to basically get these distances without ever having to actually transform the points into a higher dimensional space. Okay, so let me illustrate how this works. Okay, so we're going to do kernelized k-means clustering, and it works like k-means clustering, except we don't actually have to calculate the locations of the centroids itself. Okay, so normally we would find the location of the centroids and we would take the distance to each centroid and then reassign based on that. But now we have a formula to find the distance to the centroid without actually knowing the location of the centroid, right? This seems so crazy, or I don't know. Maybe it's not apparent. Maybe it's like I just showed all of these double summations and you're just like, okay, and I'm telling you, oh, this is amazing, and you just, but this tells us the distance point n is to centroid K, but in this formula, there's no actual calculation for centroid K, all right? Whereas back here, this like makes sense. The distance to centroid K is you take xn, you have centroid K, you do what's the difference there, and then you square that, okay? But we are getting this same distance without actually figuring out what this centroid location is, okay? And so here's the distance. And so kernelized k-means clustering just says, okay, start by randomly assigning them, and then reassign the values to the nearest centroid using the kernelized distance. We didn't actually have to calculate the centroid there, okay? And then you just repeat that step, okay? You just reassign the points and then recalculate distances, okay? Reassign the points, recalculate distances, okay? Don't actually need to calculate the centroids themselves. So let me just illustrate this. We're going to start off with a very simple data set, and I'm going to do the same thing twice. First, we're going to take my two-dimensional data, and I'm going to actually transform it into 3 dimensions. And then we will actually calculate the locations of the centroids, find those distances, and reassign the points, okay? And this is just to kind of, I don't know if this is convincing, and I don't know if the next things I do will be convincing, but the point of it is to try to convince you that this formula is actually accurate, okay? That we can get the distances to the centroids even though we didn't actually calculate the centroids themselves, okay? Because what I'm going to do is I will actually calculate the centroids and calculate the distances to the centroids, and you can actually see that calculation. And then I will get that same number even though in my second attempt when I don't calculate the centroids, okay? if you can follow what I just said here. All right, so in the first run, I transform the data into the higher space and we calculate the centroids and calculate those distances. And then the second run, I'm going to just use that formula directly to get those distances without actually calculating the centroids. Okay, so toy data set. This is my coordinates. I've got 4 points here. 0.1, 0.1, 0.1, negative 0.1, negative 0.1, 0.1, negative 0.1, negative 0.1. These are the 4 points right here. And then I've got 2, 2, 2 minus 2, minus 2 minus 2, and minus 2, 2, which are the 4 points outside. And what we're going to do is we're going to do k-means clustering, but kernelized, okay? And this is an example where if I said cluster, find some structure and find 2 clusters, how would you do it? You would probably put these 4 in one cluster and then the outer 4 in another cluster, right? There's something conceptually that says that makes sense, right? But if we did k-means clustering and we said points that have small Euclidean distance are close, similar to each other, and points that have big Euclidean distance are different from each other, then according to regular Euclidean distance, this point is super different from this point, okay? And so this point up here and this point down here would never belong to the same cluster, okay? Although when we look at this, I don't know, like spiritually or something, we feel like those outer 4 belong like they're like family or something, okay? And so regular Euclidean distance would never cluster the 2 distant corners from each other, because that's going to say, hey, those are super far away, okay? So what I'm going to do is I'm going to apply this transformation function, and it's going to be x1, x2, and the third coordinate will be x1 squared, x2 squared. And so here I transform it from 2D into 3D, and I get 0.1, 0.1, and then if you do 0.1 squared plus 0.1 squared, you get 0.02. And then if I do the same thing for these points down here, 2, 2, and 2 squared plus 2 squared gives me 8. Okay? And so this is what we get. And right now I just have random assignments. These 0.1, 4, and 8 are assigned to cluster 1. And by random chance, points 2, 3, 5, 6, and 7 get assigned to cluster 2. And so I plot this, and this is what it looks like. It's hard to see. Let me... Okay, so this is the plot, and then I say, okay, let's take the, and it's really hard to see on the projector, but this point is red, this point is red, this point is red, this point is blue, and then I've got 2 red points down here and 2 blue points down here. So we're going to find the centroid of the 5 red points and the centroid of the 3 blue points, okay? And this is the centroid of, I think, the 3 blue points, and this is the centroid of the 5 red points. Here is a plot of those things that I can actually rotate, okay? So here I've got 1, 2, 3 points that are red up top and 2 points that are red on the bottom, and then I've got 2 points that are blue and 1 point that's blue over here. And so the centroid, so, you know, looking top down, you can see that, okay, these 2 blue points, this blue point, the centroid is going to be there. These 3 red points and these 2 red points, the centroid of the red points is there. And then, you know, if you change the, I don't know, okay. but you can kind of see what's happening here. So we have the center of these 5 red points is right up here, and the centroid of these 3 blue points is down here, okay? And now we are going to do k-means clustering, okay, using regular Euclidean distance now that we've projected it up to 3D, and we're going to say, okay, which centroid is closer? So we're going to ask this point, which centroid is closer for this one? Is it the red one or is it the blue one? And I think the red one is closer, and we reassign it to whichever centroid is closer. And so what we're going to find is these 4 points, this centroid is closer, and for these 4 points, this red one is closer, and then we're going to do our k-means clustering that way. Okay, so so this is again in 3D, it's difficult to see when it's flat here, but when you can kind of rotate it, you can kind of get the idea of where these centroids are. The code to create it is right here, so you can use plot 3D RGL. And apparently I need to update my R version, okay? And it will plot the thing. Okay, but just to illustrate, so the coordinate of centroid A, which was the blue one, is negative 0.667, 0.667, and 2.68. And then the very first point, which is one of the points on the bottom, that coordinate is 0.1, 0.1, and 0.02. And then so you say, okay, well, what is, the difference in x1? So you have 0.76. What's the difference in x2? You get 0.566. What's the difference in x3? You get 2.66. And then you square all of those things, and then you add them up. And so the distance from the first point to the first centroid is 7.98. Okay, so you just take, x1 minus x1 squared, x2 minus x2 squared, x3 minus x3 for the two different points. You square them, you add them up. So this is the squared Euclidean distance from point 1 to the centroid of cluster A. And I do the math for all the distances from point 1 is this centroid of cluster A, point 1 to the centroid of cluster B. And then, so I do this for all 8 points. I do that and calculate the distances to all the centroids for all 8 points for cluster B. And then when we do this, we say, okay, which distance is smaller? Okay, the distances to centroid A are smaller. So for these 4 points, they get assigned to cluster 1 or centroid A. And then for these 4 points, they get assigned to cluster B, centroid 2. Okay, so I only did it for this one point, but you can get the idea and calculate the distance from each of these things, each point to each centroid, to redo the assignments here. Okay, and so these are the distances to the centroids. We calculate the assignments. So pay attention to these numbers. Distances to centroid A are 7.984, 8.251, 7.718, 7.984, 37.191, 42.525, et cetera. Okay, I'm going to recreate these distances using the kernelized formula without calculating the coordinate of the centroid. All right, let me give you your second view quiz answer, which is the letter B. B as in bear. B as in bear is your second view quiz answer. Okay, and so when you recalculate the centroids for the points, so after you redo the assignments, you recalculate the centroids, you get this, which is not very exciting, but let me go ahead and do that. Okay, so, oh, is that not it? This didn't, oh, never mind. Okay, well, anyway, the idea here is now you have the top 4 points up here are all red, and the centroid is basically the center of the box on top. And then all 4 points on the bottom are blue, and the centroid is right in the middle of those 4 points at the bottom. Okay, and so the k-means clustering is performs as we would expect. Okay, and if you recalculate this, then the coordinates of the centroids are now 0.02 and 0, and 8.0, and so the distances to centroid A is super small, and the distances to centroid B are super big for the first 4 points, and the distances to centroid A is very big for the last 4 points, and moderately much less for these. So our assignments don't change, and we'd say it has converged. Okay, so I want to recreate the values on this slide. I guess it's slide 36. On this slide, I want to recreate these values without actually having to calculate what is the coordinate of centroid A and what is the coordinate of centroid B. Okay, and we're going to use that using this formula. Okay, and the kernel function is, all of these points exist in 2 dimensions, right? XA is a 2-dimensional coordinate, XB is a 2-dimensional coordinate. We're not going to transform anything into the higher dimensional space. We're just going to use the kernel function. And so, implementing this formula is a bit of a pain to do, but it can be done and it doesn't require any transformations here. So we're going to take all of our things. We're going to start off with the same random assignments, okay, where points 1, 4, and 8 belong to cluster 1, and the other 5 points belong to cluster 2. And so ZA will be 0s and 1s for cluster 1, so it'll be 1, 0, 0, 1, 0, 0, 0, 1. And cluster B will be 0s and 1s, but for cluster 2, so it'll be 0, 1, 1, 0, 1, 1, 1, 0. Okay, so I'm going to figure out this kernel matrix, which requires us to find we apply the kernel function, okay, for every kind of combination of points M and R, okay? So this requires me to do a double sum to kind of create this big kernel matrix. We're going to apply the kernel function to kind of every, I've got 8 points here, so I'm going to have an 8 by 8 matrix where we're going to say, okay, what's the kernelized function applied to point 1, point 1, point 1, point 2, up to point 8, comma, point 8. And so this gives me this 8 by 8 matrix. And, it's hard to make too much sense of this directly, okay? But this is the kernelized function for basically all possible pairs for points A and B. And that's going to play a role, when we try to calculate this double sum, and we'll do it for, kind of all of these things here. All right, so for the double sum, we're going to take all of those things, and we're going to just do Zm times Zr. Okay, so basically, only when M and R are both 1, when we do this double summation, are we going to add that kernelized distance. And so I start off with 0, and I kind of go through every value of R and every value of M, and I get this whole thing. Okay, there's you can actually avoid the double sum by kind of taking advantage of a little bit of stuff, and you can get the same value this way. But basically, we're just applying this formula here to get the summation of all of these things. And okay, and so now the distance from N to K, all right, is we're going to do kind of the kernel for N comma N, 2 over N, and we're going to look at the sum of each of these things, okay? And when we calculate these distances, okay, from point N to centroid, the first centroid, the values I get are exactly the same values that I had on a few slides ago. So I have 7.984, 8.251, 7.718, and if I go back to slide, I guess 36, we can see we have those same values, 7.984, 8.251, 7.718, and so on and so forth, okay? So, with a kind of a little bit of, I guess, summation magic, we are able to calculate the distances to the centroids, even though nowhere in this formula the coordinate of the centroid itself actually appears. Right? And that's going to be very helpful when we want to use some kind of kernel function where the equivalent transformation puts it into infinite dimensions. So if you use the radial basis function, the the phi transformation technically projects your two-dimensional coordinate or your whatever point you have into an infinitely long vector. And so, what is the location of the centroid in this infinite dimensional space? You're not actually going to be able to calculate that out. But we don't have to. We can just get the distance to that centroid, wherever it is, by using this formula. So we can just get the distance to the centroid, even though we don't actually know where the centroid is, which is kind of cool, okay? And so we do this, we get the distances to centroid A, and you'll see these match exactly. It's actually slide 36 that we have, okay? And then I can do the distances to centroid B, and I get the exact same distances. So you can look at this, 23.265, 23.105, and if I go back, 23.265, 23.105, 23, so on and so forth, okay? So I don't know if this is convincing at all, but the idea being we are able to get these distances, even though as part of the formula, we never actually found the location in this higher dimensional space, okay? And then so once you have these distances, then you just say, okay, well, which centroid has the smaller distance? So we say, okay, here's the distance to centroid A, distance to centroid B, and we say, okay, these 4 points will get assigned to centroid A, these 4 points will get assigned to centroid B, and we do our k-means clustering that way. So we still assign them to the nearest centroid. It's just we don't actually know where the centroid is. We just know the distances to the centroid. Okay. And I think I did more stuff to kind of say, all right, let's redo this again, and we can still get the distances to the newly calculated centroids. Again, we don't actually calculate the coordinates of the centroids. I just redid the work, and we still say, okay, now that we've reassigned the points, what are the distances to the new centroid? And we get the same values that we had, okay? And so these are the distances to the new centroid, even though we never actually calculated the new centroid or the points in this higher dimensional space. All right, and so here's just another example where this is just a fictional data set. I got these points here, and again, using regular k-means clustering, where we use Euclidean distance, it would never put points over here in the same cluster as points down here, because these are far away. But when we do kernelized k-means, this will project it to a higher dimensional space, and we will form a cluster in the center and a cluster in the outer ring. Now, for this So if I do k-means clustering, this is the result that it gets, okay? It says these points belong to the same cluster, and these points up here belong to the same cluster, okay? And it doesn't put any of these points in the same cluster as down here because according to just Euclidean distance, the points up here and these points down here are very far apart. Okay, so for kernelized k-means, here I'm going to use a Gaussian kernel, just for fun, okay? And so the Gaussian kernel basically does e to the e to the difference between m and r, okay? And so we're going to have a Gaussian kernel. I'm going to start off with kind of just random assignments, and I'm going to go through this. Again, the Gaussian kernel technically projects our data into this infinite dimensional space. And so we're not able to visualize or graph that or even calculate a centroid because the coordinates of all of these points in this projected space have infinitely long vectors. Okay, so the first slide, this is the random assignments. I just randomly assigned some to red and some to black. And what you're going to see is you're going to see the clustering algorithm working but it's just going to be weird. Okay, it's just going to look weird because the data exists in this infinite dimensional space, and we're just projecting it back down into 2D. Okay, so this is the work, and so after one iteration, it reassigns some of the points to one cluster to red, and other points to black, and this is kind of the assignments. And as I iterate, now all of everything on some on the outer ring, these points are black, these points are black, these points are black, and these points are black. Everything else in the outer ring is red. The center is kind of half red, half black. And then as I do another iteration, now everything on the outside is red, and the center is kind of a mix, and I do a few more iterations. And then we finally reach convergence where the center, all the points in the center get assigned to the first cluster black, and all the points in the outer ring get assigned to the second cluster red. It's hard to make sense of what exactly is happening, but all we have to do is we just trust that it's projected into this higher dimensional space. The centroids exist, although we don't know the coordinates there, and we're recalculating the distances. Okay, let me give you your last view quiz answer, which is the letter C. C as in cat. C as in cat. Okay. And so it's a little bit weird to think about this, and I don't know if this is even a fair example as kind of how you can think about this, right? But let's say you wanted to cluster actors, okay? You wanted to put some actors together, all right? And so here we have Chris Evans, Chris Hemsworth, and Jason Momoa. And I don't know if you're familiar with everybody, but we have Captain America, Thor, and then Jason Momoa from Game of Thrones or Aquaman. And we might cluster these three actors together or something like that, okay? Now, how does such a cluster exist, right? Because a person is this complicated thing, and so how do you measure, what is the centroid? If you think about what is the centroid of this cluster, it's, some fictional, non-existent person that plays superheroes, or I don't know. I don't know how you would describe the centroid of these three. Okay, versus I've got three other actors here that play different roles, different types of characters, and different types. So this Joseph Gordon-Levitt, Jesse Eisenberg, and Kumail Nanjiani, and their kind of roles are different. And again, what is the centroid here? And again, the centroid is kind of this undefined, impossible notion to imagine, that might exist in some weird high dimensional space. But if you were to get like a new point and ask and say, hey, try to create a cluster, try to cluster this character in with, or this actor in with some of these other clusters, what you might be able to do is you might be able to kind of compare. So Chris Pine, I guess, is plays different roles, Kirk in Star Trek, and among other things. Okay, you might kind of say, well, how similar is this actor to any of these other actors, right? And by kind of doing a comparison between actors to actors versus trying to figure out what the centroid is of these people, you might be able to kind of cluster them accordingly, right? So it's a little bit strange to think about, but you're mostly doing kind of by doing the inner product here, which is, again, it's difficult to make sense of just this matrix, but by taking the inner product, now we have some kind of measure that is a comparison of one point to another point, okay? And so you're just doing comparison of points to other points to kind of get a sense of the structure within your data there. Okay, so that's kernelized. K means clustering, and I think you have a little example of it in your homework to work through. I hope this kind of makes sense, and so we'll end here for today, and we will see you on Friday.